So in the previous video, we noted that any linear transformation that is turning some vector into some other vector can be represented using a matrix. And in today's video, we're going to practice finding the matrix representing some of the most common types of linear transformations. So to begin with, let's go ahead and find the 2 by 2 matrix that corresponds to the action of rotating vectors in two-dimensional space, specifically taking a vector and rotating it counterclockwise through some angle, which we will just call theta. As usual, if we want to find the matrix corresponding to a certain transformation, all we have to do is figure out what would happen if we applied that transformation to the two standard basis vectors for, in this case, two-dimensional space. So let's begin by taking E1, the first standard basis vector for two-dimensional space, and seeing what results when we apply this transformation to it. E1 is going to start out pointing 1 unit in the positive x direction. And then after we apply this transformation, it's going to end up being rotated through an angle of theta. So let's imagine that angle theta is this. The result of the vector after the transformation is applied is somewhere over here, maybe in quadrant 2. So what would be the coordinates, what would be the components of this vector that result after transformation has been applied? Well, the result would just be in terms of sine and cosine of this angle. Cosine of theta would be our x component, and sine of theta would be our y component. Now, let's consider what happens if we apply that same transformation to the second standard basis vector, E2. If I apply this transformation to E2, the result is going to end up graphically somewhere maybe in quadrant number 3 if the angle theta is this large. A couple of different ways to go about doing this. I think for me, the thing that occurs first is to recognize that the total angle between this final vector and the positive x-axis is going to be theta plus pi over 2. So that means that the coordinates of this vector, the coordinates are going to be cosine of theta plus pi over 2 and sine of theta plus pi over 2. Sine and cosine of the angle that this vector makes with the positive x-axis, which is pi over 2 plus theta in this case. But that can be simplified using some of the properties of sine and cosine. So for example, you could use the angle sum identity for sine and cosine to clean this up a little bit. If you don't remember the sum identities for sine and cosine, I don't blame you, but we can just look them up. So for example, the ones that I'm thinking about using are these first two here given in this picture, where it says cosine of angle alpha plus angle beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And sine alpha plus beta is the same thing as sine alpha cos beta plus cos alpha sine beta. I'm going to go ahead and apply these two formulas to my specific instance where the alpha is this angle theta and the beta is pi over 2. So for example, if I apply that here, I'll get cos theta cos pi over 2 minus sine theta sine pi over 2. And in the bottom row, sine theta cos pi over 2 plus cos theta sine pi over 2. Now, sine of pi over 2 is 1. Cosine of pi over 2 is 0. And if I use that in the simplification, I get a result of negative sine theta, and I get cosine theta. So this would be, after simplification, what results when we apply this transformation to the second standard basis vector. And now all I have to do is take these two results and use them to build my matrix by using these vectors as the columns of the matrix. Cos theta, sine theta, and negative sine theta, cos theta. So that would be, in general, the matrix representing counterclockwise rotation of a two-dimensional vector through an angle of theta in the xy plane. So what you'll often see is that 2 by 2 matrices and 3 by 3 matrices come up as a way to encode rotation in a computer graphics context. So for example, if you're animating something for a video game or for an animated movie, one of the ways to handle three-dimensional rotation is to use a 3 by 3 rotation matrix. Let's get some more practice. Let's go ahead and find a 2 by 2 matrix that corresponds to scaling vectors. I'm going to take a two-dimensional vector and scale it by a certain factor of, let's just call it lambda. The usual process applies. So if I apply this transformation to the first standard basis vector E1, then I'm going to take the vector 1, 0, and I'm going to scale it by this factor of lambda. And so that's going to take 1, 0, and it's going to turn it into lambda 0. Similarly, if I apply that scaling transformation to the vector E2, then that's just going to take that vector 0, 1, and it's going to turn it into 0, lambda. So if we then create the matrix that represents this action, the matrix that represents this transformation, we just have to create its columns, build the matrix by using these results as the columns. So this would be the matrix representing this particular action, scaling a vector by a factor of lambda. Let's get some more practice. Another standard transformation that you'll see very often applied to vectors are things like reflections. So let's find a matrix representing, for example, reflection over the x-axis in two-dimensional space. So let's first consider again what happens to E1. If I take E1 and I reflect it over the x-axis, it doesn't actually change at all because E1 is already on the x-axis. So in this case, E1 is the same and remains unchanged when the transformation is applied to that vector. However, if I consider what happens when I take the standard basis vector E2 and I apply this reflection action to that vector, that E2 vector is going to flip down into the negative y direction. And it's going to turn what used to be a positive y component into now a negative y component, 0, -1. So the matrix representing this particular reflection in two-dimensional space would be t applied to E1, 1 in the x direction, 0 in the y direction, and then t applied to E2, which gives us a result of 0, -1. Now let's consider a problem like this, where we're asked to find the 2 by 2 matrix that corresponds to the action of taking a two-dimensional vector, rotating it counterclockwise through an angle of 60 degrees, and then reflecting that over the x-axis. So this is a pretty unique situation because the action that we're taking in this problem is a combination of two other actions that we've already studied. We have already found the matrix corresponding to rotation counterclockwise through an angle of 60 degrees. That matrix had the format cosine of 60 degrees, sine 60 degrees, negative sine 60 degrees, cosine 60 degrees. We have also earlier found the matrix representing reflection over the x-axis. from earlier 1, 0, 0, minus 1. So now let's think about what would be involved in applying these two actions back to back. If I wanted to rotate a vector x, then I could do that by taking the vector x and left multiplying it by this rotation matrix given here in green. I'll just steal it. If I wanted to subsequently then reflect over x-axis, I would take the result of this first calculation and I would subsequently multiply it on the left again. I would multiply it on the left by this reflection matrix. So I would take this result here and I would multiply that result on the left by our reflection matrix. So all of this to say is that this matrix product represents this combination of these two actions in sequence. If you first multiply by the rotation matrix on the left, and then multiply by the reflection matrix on the left, that's going to correspond to the action of first rotating the vector and then reflecting the vector. So matrix multiplication is a way to handle two actions being taken back to back. So this matrix product is going to be the matrix that represents the combination of these two actions. And if we go ahead and calculate that product using the standard dot product process, rows times columns, we can find that the matrix product results in cosine of 60 degrees from the first row times the first column. This row times this column would return negative 60 degrees, negative sine of 60 degrees. This row times this column would return negative sine of 60 degrees. And this bottom row times this right column will return negative cosine of 60 degrees. So this matrix right here, resulting from multiplying these two matrices together, would represent taking these two actions back to back.
Editor Sam here. Note the order of the matrices in the product. The matrix representing the first action is on the right. Matrices representing subsequent steps are stacked up on the left.
So that concludes today's lesson. Today we practiced finding matrices corresponding to some very common and typical linear transformations, including rotation matrices, including scaling matrices, and including reflection matrices. And then we talked about how if you have an action that represents taking two simpler actions and performing them in sequence, then that can be understood as multiplying the two matrices together that represent the two steps of your sequence.